Okay, welcome to Turning Effects of Forces Assignment 2. Alright, let's take a look at the first question now. First question asks you to state the principle of moments, okay, and it's 2 marks allocated to this. Alright, we need to know how to get these 2 marks. Okay, the exact word for word definition for the principle of moments, I'm going to leave it to you all to go and pick it up from the notes. Alright, but I'm just going to tell you where the 2 points come from. The very first point tells you, or rather you need to get the first point by telling them that, for a system in equilibrium, okay, so you're telling them essentially that in order for a system to be balanced, okay, because the principle of moments will not apply if the system is not imbalanced. Okay, so you need to make sure that to tell them, hey, for a system to be in equilibrium, this is your first point. And then the second point, you need to tell them that the sum of clockwise moment is equals to sum of anti-clockwise moment, okay, about the same point. All right, this is very important. Okay, this phrase over here, about the same point, is very important. Okay, so generally the principle of moments can be broken down into 2 parts. One is telling them that for a system to be in equilibrium, okay, the second part is telling them that the sum of clockwise moment is equals to the sum of anti-clockwise moment about the same point. Okay, question 2. The figure below shows a crane lifting some load during the building of a house. The crane has a counterweight made of concrete which balances the load during lifting. Okay, so as you can see, the counterweight is acting in this direction. The load is acting in this direction. So the pivot is here. This is the pivot. So the counterweight acts and creates a clockwise moment, whereas the concrete, the load, okay, it acts with a clockwise, anti-clockwise moment. So calculate how far the counterweight needs to be placed. All right, they're asking for this distance d. Okay, from the central support. All right, when a load of 6,000 Newton is being lifted. So in this case, okay, to lift it up, we use the principle of moment. Okay, it states what? Clockwise moment must be equal to the sum of anti-clockwise moment. So what is the anti-clockwise moment generated by the load? 6,000 multiplied by 15, okay, is equals to 10,000 multiplied by d, right? So in this case, what is d? D will be equals to, let me do a quick one, 6,000 multiplied by 15 divided by 10,000. Okay, that would be 9 meters. Okay, this is the answer. Very simple and straightforward. Question 3. AB is a uniform rod which balances at the 50 cm mark on a knife edge. Okay, so let's talk about knife edge. This is basically telling you that it's a point, very sharp point. So it acts as a perfect representation of pivot, okay, because pivot has to be supported at only a single point, all right, not over a region. Calculate the value of x, all right, calculating the value of x. So one thing that I want to bring up about in this question is do not take the values given to you directly, okay. You need to know that to calculate moment, we are always talking about what? Moment is equals to force times perpendicular distance. Okay, perpendicular distance, so we're talking about the difference, all right, because the 20 cm and 85 cm is telling you, at that position, at that exact position. Okay, they're not giving you the distance. So to find the distance, we need to make sure we subtract. Okay, so calculate the value of x. So same thing, because it's balanced, so this is already in equilibrium. We use the principle of moment to solve this question. So this is a anti-clockwise moment, this is a clockwise moment, so it's 100 multiplied by, this is 30, right? 50 minus 20, 30 cm, okay, is equals to what? X, all right, multiplied by 85 minus 50 times x. Okay, so of course you can do it separately and put 30 cm here, and then over here you can put 35 cm, it doesn't matter. Okay, so for this question, because we are not required to find everything in SI unit, okay, we can just use centimeter to solve throughout the entire question. Okay, so in this case, what is my value of x? So I have 3,000, okay, over here is 3,000, right? Then 3,000 we divided by 35, so this is 85.714 Newton. Okay, we wrote it off because it's not a perfect answer. Round it off to 3SF. Okay, 85.7 Newton. Okay, question 4. A uniform meter rule. So usually I'm gonna highlight uniform means it will, the weight will act at the 50 cm mark. All right. So in this case, because the pivot is also at the 50 cm mark, the weight of the ruler will not affect or will not create any moment. Okay, balance at the 50 cm mark. So weights of 1.5 Newton, 3 Newton are hung from 10 cm, 40 cm marks respectively. So another weight W hangs from the 80 cm mark. They want you to calculate moment about 50 cm mark due to 1.5 first. All right, I'm not going to care about the 3.0. I'm not going to care about the W yet. I'm just going to take a look at the 1.5. So how to find moment? Always the same. Moment equals to force times perpendicular distance. 1.5 multiplied by 1. What's the perpendicular distance? Is it just 10? Okay, so be very careful. Do not use 10. It's supposed to be 50 minus 10. Okay, we're finding the distance here. 40 cm. Okay, so answer is 1.5 times 40. I get 60 Newton cm. Okay, this is very important. Do not put Newton centimeter. Do not put Newton meter. All right. If you put it that way, you thought it's SI unit when you did not use the SI unit to calculate. A wrong unit will not give you the correct answer. Okay. The value of the weight W. Okay. So in this case, now we are talking about the entire system already, right? So W gives you a clockwise moment. This 3 Newton gives you anti-clockwise. This 1.5 gives you anti-clockwise. So according to principle of moment, sum of clockwise must be equal to sum of anti-clockwise, right? So the sum of anti-clockwise is these two. All right, let's find. 1.5 times 40 we already found, right, is 60. Plus the anti-clockwise due to 3 Newton will be 3.0 multiplied by, in this case is 50 to 40 cm mark to the 50 cm mark is 10 cm, right? All right. This is the anti-clockwise moment. Okay, it must be equal to the clockwise moment. So clockwise moment will be, what is the distance? 80 minus 50, right, over here, multiplied by W. Okay, I know many of you do not like to play around with long equations. You all like to do it one part by one part. You want to find the anti-clockwise moment first, then after that you find the clockwise, then you do another step to equate them. It is fine by me, but usually I would like to compress everything in one line, because I know the more lines I write, the more careless mistake I may commit. So please try to get yourself better at this, hone up your mathematical skills as well. Okay, so left hand side, what is it? 60 plus, this is 10, 10 times 3 is 30, right? So this is 90, is equals to 30 W. So W is 3.0 Newton. Okay, why do I bother putting 0.0? Okay, why can't I just put 3 Newton, since that's what the value, the value that the calculator gave me, right? Okay, because the question actually gives you everything in 2SF. All right, so I will just follow the accuracy of the question. Question 5. A uniform meter rule has a mass of 90 gram. Okay, 90 gram. Center of mass 50 cm mark. The diagram shows its ruler suspended by a thread at the 70 cm mark. I know there is no diagram given to you, but you can draw the diagram on your own. Okay, let's draw it. Balanced by a mass of weight W hanging by the 80 cm mark, right? Okay, let's draw now. This is a meter rule, 1 meter. Okay, center of mass is at 50 cm mark. Okay, suspended by a thread. Okay, so let's say this is 0, this is 100. 70 cm mark, let's say it's here. Suspended means it's hanging. Hanging means this is actually the pivot. This is actually at the 70 cm mark. Okay, because it's uniform, it means that the weight will act in the center. Center means at the 50 cm mark. This is the weight. So this is the 50 cm mark. All right, but the question did not give me the weight. It gave me the mass. So we need to do the conversion later. Okay. Any other thing? Balanced by a mass of weight W. So at the 80 cm mark. Down here is W, 80 cm mark. Okay, so now we have all the figures. All right, let's do a quick one. Okay, shall we find the weight, okay, of the ruler? 90 gram, right? W equals to mg. Okay, be very careful. Convert the mass to kg first. All right, times 10. So it's 0.90 Newton. This is 0.90 Newton. Okay, now we have the force. All right, and we are told that it's balanced. So we can find the answer, find the value of W using the principle of moment, right? Sum of clockwise moment equals to sum of anti-clockwise moment. Okay, so the anti-clockwise is 0.90 times 5. Oh, oops, sorry. This value, okay, is 70 minus 50. Careful, don't use the 50 directly, okay, you're going to get it wrong. Equals to, over here is 80 minus 70. Okay, W times W, right? Okay, so let's do it now. 0.9 times, what is this? This is 20. 0.9 times 20, you get 18. Is equals to 10 W. W equals to 1.8 Newton. Simple. Okay, let's move. 6. Calculate the total clockwise moment in this figure. Alright, so let's take a look and analyze. Looks complicated. Alright, so basically there's a F that is acting upwards. This is a, what is this? This is an anti-clockwise moment, right? And then we have a 40 Newton acting downwards. The pivot is here, so it will cause it to turn in this manner. This is actually a clockwise moment. Okay, we have a lot of distance given to us. We have a 3 meter, okay, we have a 13 meter, 5 meter, 1.5 meter. So we need to, in order to get this question correct, you must be very clear, okay, very strong with the fundamentals and understand the definition of moment, okay, which is the product of the perpendicular distance between the applied force and the applied force itself. Okay, so how do we calculate the total clockwise moment? Clockwise moment will be just 1 due to the 40 Newton, right? So it's just moment equals to force times perpendicular distance. Force is very straightforward. I'm given 40 Newton. So what is the 40? What is the perpendicular distance? Is it 3 or is it 1.5? Okay, we are using the 1.5, right? Because the 40 Newton is acting downwards. Perpendicular distance, perpendicular to down, which is a vertical direction, is actually the horizontal. So we're looking at 1.5 meter. 1.5, answer is 60 Newton meter, because everything in terms just nice, Newton and meter, right? So they want you to calculate the value of F given me using the principle of moments, because let's say this is considered as balanced. Okay, it's not tilting, it is held in this position. So how do I find? Okay, so I'm going to use the clockwise moment equals to anti-clockwise moment, right? So previously we already found the clockwise moment, which is 60 Newton meter. Okay, anti-clockwise must be due to the F. We already said, established the fact earlier on. So F times what? The perpendicular distance. Is it 13 meters? There's another distance at the bottom, which is 5 meters. So like I said, F is a vertical force also, right? So the perpendicular distance should be this. Okay, this distance is not 90. So we're not going to use the 13 meters. So it's 5 times F, 5F. F is equals to 12 Newton. Alright. Question 7. A spanner is used to release the bolt. The minimum moment required to turn the bolt is 20 Newton meter. 20 Newton meter. So a single force F1 is applied to the spanner as shown. Okay, so I'm going to ignore the F2 first. Just take a look at F1. So in order to turn the bolt, alright, what must my value of F1 be? So what is the moment needed to turn the bolt? They told you it's 20 Newton meter. So that must be the minimum moment that my F1 needs as well. Okay, so in this case, the moment that is generated by my F1 must be 20 as well. So F1 times 20, but careful, over here is 20 cm. In the question, it says Newton meter. So we will need to change the value of the distance to meter in order to be consistent throughout in terms of units. Okay, so F1 times 20 over 100, okay, must be equals to 20, right? The two moment must multiply, the two values multiply to give you at least 20. So what is F1? F1 will be equals to, okay, 100 Newton. Okay, so in order to turn a bolt, I need to apply a force of 100 Newton. Okay, so now part B, they tell you that a second force F2 is applied together with F1. Okay, they give you another force to help you to turn the spanner, and they are telling you that both F1 and F2, they are equal in magnitude. Values are the same. F1 and F2 are equal in values. Okay, so in this case, I have two forces, and these two forces are giving me clockwise moment. All right, so in this case, I can add them up, right? So what is the force needed then? Okay, so let's do it. To turn it, I need 20 Newton meter, right? So I have F1, remember everything I must convert to meters, okay? But my F2 distance is not 10 cm, my F2 distance is 30 cm. That one you need to be very, very careful, okay? So 20 over 100 times F1 plus 10, oh, you see, 30 over 100 times F2, okay? So be careful because they already say both forces have the same magnitude, right? So let's call F1 and F2, they're the same. We just call it F, all right? So that, since they're the same thing, I should only assign one algebra to it, okay? If not, they're going to confuse me. So in this case, it's just 20 over 100 F plus 30 over 100 F. So since they're both F, all right, I can just simply add them up, which is 50 over 100 F. 20 is equals to 50 over 100 F. 50 100 is half F, right? So in this case, F is equals to 40 Newton. That's it. Okay? I can turn the spanner if I have two forces and each at 40 Newton. C. Explain why a longer spanner requires less effort to turn the bolt. Okay, so now imagine I have a long spanner now. Okay, so why a longer spanner will require less effort? Okay, so you see, moment is equals to force times perpendicular distance. The moment to turn the bolt is in this case the same because the bolt is the same, right? So it's 20. Let's just put in some random numbers to generate so we can see clearly. Okay, imagine the distance was 5. Okay, the distance is 5 meters. So how much force do I need? I only need 4 Newton, right? 4 times 5 is 20. So in this case, let's say I'm going to use a longer spanner. Okay, this is scenario 1. Scenario 2, same bolt, so I still need 20. But now I use a longer spanner. Let's say I use a spanner that is 4 times the length. Instead of 5 meters, my spanner is now 20 meters. It's a humongous one. Alright, so how much force do I need? I only need 1 Newton. So this example has clearly shown that a longer spanner does help us to open up the bolt because less effort is needed. However, alright, it does not make any engineering sense if let's say my spanner is 20 meters long. Alright, imagine a 20 meter spanner. How are you going to carry it around with you if imagine you're a technician or engineer? Right, it does not make any sense. So there is always a sweet spot. Okay, we want to make sure that less effort is needed, but at the same time, we do not want to compromise on the usability of the tool. Okay, so of course we're not going to explain using the random numbers like this. We need to explain in terms of words, right? So we just need to show the formula first. Okay, then you just tell them that a longer spanner has a longer perpendicular distance between the applied force and the pivot. So what? Alright, so we already proven using the numbers, right? Okay, so we just have to say that larger perpendicular distance will require a smaller effort. In this case, effort refers to force, okay? To generate or create the same moment to turn the bolt. Okay? Alright, I hope this explanation is clear. Alright, and take note, in this assignment there are a lot of questions that requires very similar explanation. Okay. Question 8. An airline passenger places his baggage of mass 50 kg. Okay. Mass is 50 kg onto a trolley as shown below. He applies a force F at the handle to raise the cases to the horizontal position shown. Okay. So look out, they are all in millimeters. Okay. Is there a need to change? Alright, we'll take a look at the question. If the question does not require, then there is no need to change. Okay. So on the diagram, draw an arrow to represent the weight of the luggage. baggage. Okay, so in this case, the baggage we can assume, all right, the weight is evenly distributed. So if the weight is evenly distributed, the weight should apply, or the CG should fall at the geometrical center of the entire baggage center. Okay, remember to label. Okay, weight. The axle of the wheels acts as a pivot. Axle is here. Okay, for those of you who don't know. Calculate the moment of the weight of the luggage about this axle. Alright, so they're finding the moment due to the weight of the baggage. Okay, nothing to do with the F first. So in this case, you see, weight is how much? Moment is equals to force times perpendicular distance. And perpendicular distance is, okay, wait, let me find the weight first. They were given a mass. So in this case, we need to change the mass to a weight, right? 50 times 10. That's the weight. All right, multiply by what's the distance? Okay, so since it is at the geometrical center, they only gave us the width of the entire baggage. The geometrical center will let us conclude that the distance between the CG, the weight, and the pivot is 200 mm. Alright, so just multiply by 200 mm. Doesn't matter because the question never required us to change it to SI unit. So I'm just going to happily use 200 mm to find the answer. So it's 50 times 10, 500 multiplied by 200. I have 100,000 Newton millimeter. Can I actually change it to Newton meter or centimeter? Newton centimeter? Yes, you can. All right, although the question does not require you to, you can. All right, you just have to convert your 400 mm, sorry, your 200 mm to cm, which is 20 cm, or you change it to meters, which is 0.2 meters. Okay, that's additional step on your side. All right, so you're not given marks for the conversion, but should you convert it wrongly, let's say 200 mm, you somehow say that it's 2 meters instead of 0.2 meters, you're gonna get the entire question wrong. Okay, probably just given a 1 mark for the correct equation, the formula. Okay, C. Calculate the F required on the handle to keep the luggage horizontal as shown. Okay, so according to principle of moment, okay, so your F, the pivot is here, right? So your F will create a anti-clockwise moment. Your weight will create a clockwise moment. So we're going to equate them. Okay, so 100,000, this is the moment due to the weight of the baggage, must be equals to the moment due to the F. So in this case, it's distance times F, right? 1,000 times F. So F will be equals to 100 Newton. So you see, I only need to exert a force of 100 Newton, okay, to lift the weight of a 500 Newton baggage, okay, up. So that's the magic of this trolley, right? The design. You see, D, they ask, explain how the design of the trolley allows the person to use less effort to lift the luggage. Okay, so in this case, this is the same kind of explanation that we're going to give. Okay, the perpendicular distance between the handle to the wheel axle is larger than the perpendicular distance from the CG of the luggage to the wheel's axle. So I'm going to write this here, all right, so that you don't have to refer. So what if my perpendicular distance is larger? Then the force required or the effort required is less. Therefore, the effort, which is force, needed will be less, okay, to create the same moment to lift the baggage. Okay, baggage, luggage. All right. So this is where the 2 marks come from. Question 9. The figure below shows a stool. A horizontal force F keeps the stool balanced. C is the center of gravity of the stool, and the weight of the stool is 30 Newton. Okay, so it's a bit unclear. C is here. All right, I'm going to write a big C here. Okay, that's where the CG is. Okay, and the weight is 30 Newton. Pivot is right at this point here. This is where the entire stool balances on. Okay, so that's 6 cm away from the CG. Okay, and then I have a horizontal force F that keeps the stool in position, and it's 40 cm away from the pivot, perpendicular distance, right? Calculate the moment of the weight about the point P. All right, moment of the weight. So we're only talking about the moment due to the weight. All right, nothing else. Ignore your force F for now. So moment equals to force times perpendicular distance. Force is 30 Newton. Perpendicular distance is 6 cm. 180 Newton cm. Okay, remember it's Newton centimeter. Do not write Newton meter. Okay, because you calculate using cm, not m. Calculate the value of the force F. So in this case, the force F actually held the stool in position, all right, in equilibrium. So we're going to use the principle of moment to solve this question. So we already know the moment due to the stool, right? 180 must be equals to F times 40, right? So F is equals to 4.5 Newton. Very simple, you see, 2 marks. Question 10, the figure shows a claw hammer being used to pull a nail out of a piece of wood. Okay, so where's the pivot? This is the point, right? So the pivot should be somewhere here. Okay, explain why the force at the nail is greater than the force exerted at the handle. Oh, why? This is the perpendicular distance, right? The pivot is here, so the force is here. So this is the perpendicular distance. And then there is another force due to the nail is here. This is the perpendicular distance. Is it obvious now? All right. So you see, very similar explanation. Why the force at the nail is greater? The perpendicular distance between the handle and the pivot is larger than the perpendicular distance between the nail and the pivot. Okay, larger perpendicular distance. So write this down again so that we can have a clearer understanding. So what if the perpendicular distance is okay, so we are talking in terms of nail, right? So what if the perpendicular distance is smaller? Okay, see, all right, so therefore the force at the nail must be larger than the force at the handle. Okay, to create the same moment. Right? Okay, so you see, 3 questions back to back asking about the same thing. When the nail has been pulled out a short distance, point X of the hammer touches the wood. So point X is then the pivot. So now let's take a look at the diagram again. Everything restart. Okay, now my pivot is here. Is there a difference in the distance between the force and the pivot? No, it stays the same, right? The force, the perpendicular distance between the force at the handle to the pivot is the same. However, the perpendicular distance, at first it was here, right? Okay, I'm going to use a different color one. So at first it was here. No. Okay. This was the pivot. So at first, this was the perpendicular distance. Now the perpendicular distance between the nail and the pivot increased, right? So what does that say? Same thing. So if my perpendicular distance increase, okay, I will have a larger moment, right? Okay, since the perpendicular distance between the nail and the pivot increases, the moment due to the nail increases. right? So moment increased already, okay? So the moment needed to pull the nail out is now increased, okay? So if I need a larger moment to overcome the nail, and my perpendicular distance remains the same for the force, okay, it means that I need a larger force, okay? So since the larger moment is now needed, okay, oops, let me rephrase. A larger force is needed to create a larger moment since the perpendicular distance between the handle and the pivot remains the same. Alright, this question, the answer may seem a little confusing, okay, because we need to look at the moment due to the nail, and the next thing is we need to look at the moment due to the force and the nail. Alright, they changed. So there are two parts of this, so it might be a bit confusing. So if you cannot understand this, alright, you try to rewind and watch this part again. If you really cannot understand, alright, please come and find me. Okay, I'll try to explain in a more friendly way so that it's easier for you to understand. Okay, so yep, that will be the answer for this part. Okay, the last question is actually a HOT, a higher order question. All right, optional, but I would really suggest all of you do it because this is a 10-year series question. It's a O-level paper question. So there is no reason why anybody should not do this question. Okay, so let's take a look at it. Figure 2.1 shows the decoration that hangs by string from the ceiling in a toy shop. 4 objects, P, Q, R, and S, hang by string from rods 1 and 3. These 2 rods hang by string from rod 2. Okay, so the decoration is completely stationary and the rods are horizontal. The weights of the rods and the strings may be neglected. Okay, so this thing, I'm going to tell you to split it into 3 parts. This is one system. Okay, so we can zoom in and look at this as one system. We can zoom in and look at this as one system. And we can also zoom in and look at this whole thing as one system. Okay, how? Let's take a look at system 1, okay? Question, you see? Object P weighs 0.6 Newton. So this is 0.6 Newton. And object Q weighs 0.16 Newton, right? Okay, so let's look at the blue box, my system 1. Okay, so I'm just going to redraw everything. So over here, it's like that. This is P, this is Q, right? P is 0.6 Newton, Q is 0.16 Newton. This is distance D, and this is 4.0 cm. Okay, so they want you to calculate the value of distance D. Alright, so what is D? In order for this entire thing to balance according to principal moments, right, the sum of clockwise moment must be equal to the sum of anti-clockwise moment, right? So let's take a look now. So how do we calculate? 0.60 D is equals to 4.0 times 1.6, right? Okay, I thought this is pretty straightforward. So D will be equals to 4 times 1.6, entire thing divided by 0.6. Okay, let me try again. 4 times 1.6. Oh, no, not 1.6. Times 0.16, right? Okay, 4 times 0.16 divided by 0.6. So answer is 1.0666 cm. Round it off to, you see, they actually give it in terms of 2SF, right? Everything in 2SF, 0.60, 0.16. So I'll just leave it in 2SF, 1.1 cm. Okay, that will be my D. They want you to determine the weight of R and of object S. Okay, so to do this, right, although R and S, they seem to be like from just the red color system, the red box system, we should actually look at this entire thing in terms of the green box. Okay, this is actually the harder question, all right, that makes this a higher order thinking question. So let's do this together. I'm going to redraw everything. Okay, I'm going to redraw everything. 10 cm, 10 cm. So I have a string. This is 10 cm. This is 10 cm. Okay, and it's hanging down. All right, holding on to rod 1 and rod 3, right? Okay, but I'm going to comprise. I'm just going to compress everything. My rod 1, my P and Q into a single weight. Okay, I don't care what's happening over there, but I do know that over there I have a total of 0.6 plus 0.16 Newton. So over here there's 0.76 Newton. Do you agree? Okay, P and Q add up 0.76 Newton. So over here I also have the total weight due to R and S. Okay, but the thing is, how do I do R and S now? So just look at this entire system that I just drew. Okay, they are equidistant from the pivot, which is this line. If this is 0.76, what do you think this value must be? Right, it has to be the same, which is 0.76. In order for it to be balanced, right, they must be the same weight since they are equidistant. Okay, so it means that R and S must be equal to 0.76 Newton. Agree? So you see, this is one concept that we learned and that you need to understand. So moving on, so the question is asking you not for the total mass, right? The total weight. If it is total weight, we can just put 0.76. But the question is asking you to find the weight of R and S separately. So now is the time that we're going to zoom into this rate system. So the rate system is like that. How far are they? 2 cm and 2 cm, right? 2 cm and 2 cm. Over here I have R. Over here I have S. Okay. So now I want you to take a look again. They are both equidistant from the pivot. So what does that tell you about R and S? In order for them to balance at equal that distance, right, it means R and S must both be equal weight, right? So in this case, R and S, they are the same, equals to 0.76 divided by 2, 0.38 Newton. Okay, so I would say this one, okay, if you really understood the concept, this is actually a very simple question, okay? It is the understanding that you need to have before you get these 2 points, okay? Next up would be C, object Q falls off, okay? So now let me erase this entire thing. Object Q falls off. Okay, no more object Q. State, explain what happens to rod 1 and rod 2. Rod 1 is this one, rod 2 is this one. Okay, let's take a look at rod 1. So, see, rod 1 is here, right? This system. Look here, okay? My Q is no longer around. What do you think will happen to the system? Okay, rod 1, we just tell them that the rod 1 will turn what direction? Anti-clockwise. Why? Since there is a resultant anti-clockwise moment. Right, no more Q, so no more clockwise moment. I only have anti-clockwise moment. So naturally my rod 1 will turn in an anti-clockwise moment. Okay, so rod 2 now. So rod 2, look at this. So, no, okay. So over here just now we already established, right? Down here is the same 0.76 Newton already. Okay, but over here I do not have 0.76 anymore. I only have 0.60 because my Q drop, right? Is it Q drop? Yeah. So I only have 0.6. So my clockwise moment is now larger. Okay, so rod 2 will turn what direction? Clockwise. Since there is a resultant clockwise moment. Okay, that's it. Okay, we have come to the end of this assignment. So hopefully you can understand the explanation. If not, please do not hesitate to come and find me to clarify face to face. Alright, hope you guys enjoy this tutorial.